So in this video we're going to look into the root locus problem. So this question is about find the value of k for which the closed loop system is stable and they're given the g of s, that's the open loop transfer function, is given. So I'll show you the gate problem as well. Okay. This is the gate problem. It was asked in 2017 for 2 marks and the g of s is here, right? So here it is given. That means what, it's very clear that is the open loop transfer function, right? And the closed loop transfer function would be the whole thing with the unity feedback system. That would be the closed loop. Fine. So given the g of s as the open loop transfer function is connected to a unity feedback configuration. This is the unity feedback configuration for the closed loop system shown, the whole thing, this one dotted lines. The root locus for k value between 0 to infinity. So root locus value is always from k equal to 0 to k equal to infinity. So root locus starts from k equal to 0 at the roots and it ends at the 0. If there is one root, it will go and reach the 1 0. If there are two roots will go and reach two zeros. That's all. That is how the root locus works. These basics, these are basics which we would know, or else I will explain you again, or I'll just give you the hint about all that while we solve the problem. Okay, so for now let me not confuse you much. Alright, so this k intersects the imaginary axis at k equal to 1.5. So the question says that this is the real axis sigma and this is the imaginary axis j omega axis. Alright, so in this j omega axis, somewhere k at some point at k equal to 1.5, the root locus intersects. Suppose if this is the root locus, for example, if I'm drawing, this is the root locus at k equal to 1.5, it is intersecting. Okay, it's a mirror image. With respect to the real axis, it is always a mirror image. Whatever is in the top, it will be on the bottom also. That is a mirror image with respect to the real axis, sigma axis. Okay, so at this point, this is the imaginary axis. No, when this root locus hits the imaginary axis, the value of k is 1.5. The closed loop system is stable for, we need to know for what values of k the system is stable. Okay, this is an example plot. This is not a plot for this g of s. I'm just plotting this plot is just to give the understanding of the concept in which the question is asked. So once you know this concept, you will be very comfortable to solve. That is why I just want to put this example here. All right, so according to this root locus, we have two things. One is the left side of the s plane and other one is the right side of the s plane. Okay, this is j omega is what? S equal to j omega. That's nothing but the s plane. Okay, so we are in the s plane, left side and right side. Whenever our poles come to the right side of the s plane, whenever the poles lie on the right side of s plane, the system becomes completely unstable. Whenever the poles are on the left side, when all the poles are in the all the poles on the left side of the s plane, we know the system is completely stable. Okay, when there is at least one pole in the imaginary axis, we know the system becomes marginally stable. Though we know these three conditions: marginally stable when we have in the left side as well as in the imaginary axis, it will be marginally stable. At least one pole in the right side of s plane, system gone unstable completely. Okay, with this concept we can proceed. And what we know about the root locus? Root locus is nothing but the loci or the path. It's a path of the path of the poles. So whenever the loci is on this left side of the s plane, until these values, the system will be stable. Whenever the loci moves towards the right side of the s plane, the system becomes completely unstable. That is why this imaginary axis or the marginally stable condition is very important, and that is why they given k equal to 1.5 when it hits the imaginary axis. So at this point, this is the determining or the critical point for us accordingly with respect to this question or with respect to the locus. So because for different values of k, the loci will travel at different paths. So according to the plot, this example plot that I've given, for all the values of k greater than this 1.5, it should be unstable. For all the values of k less than 1.5, it should be stable. Okay, but this is not what is the exact plot for this question. So we have to plot for this question and come to the conclusion. We have to find the loci and then see for which values of k the system is stable or not. Okay, for this let us write the g of s and find the poles and zeros. Okay, let me first find the poles. So for finding the poles, I put minus b. B is So the b is minus 3, so it becomes plus 3 plus or minus root of b square minus 4ac, that is 8 divided by 2a. Alright, so 3 plus or minus root 1 is 1 divided by 2. So the poles are 3 plus 1 4, 4 by 2 is 2 comma, and 3 minus 1 is 2, 2 by 2 is 1. So there are two poles, 2 comma 1. And then coming to the zeros again minus b, zeros we here, minus b is minus 2 plus or minus root of b square 4 minus uh, uh, b square minus 4ac, 4 into 2 8 divided by 2a, 2 into 1. Alright, so it is minus 2 divided by 2 is minus 1 plus or minus root of minus 4 becomes complex, so j, and becomes 2, 2 by 2 is 1. So the zeros are minus 1 comma plus j, sorry minus 1 plus j and minus 1 minus j. So we are having the poles and zeros. So let us plot this up. Okay, let me plot this. One pole was at one pole was at 1, another pole was at sigma equal to 2, means there was j was 0, and then poles are always represented with this x mark, and zeros are represented with this 0 mark. Okay, and and then this will be your 1j, 2j something, and here it is minus 1j, minus 2j, like that. And let me call this to be 1. So the zeros poles were 1 and 2, and the zeros were minus 1, minus 1 plus j and minus 1 minus j. So minus 1 plus j comes here, minus 1 minus j comes in the bottom. Okay, is it fine? Okay, and we know the root locus always starts from the poles and ends at these zeros. Okay, and also we know the loci exist, or locus exist in the real axis only if there are odd sum of poles and zeros to the right side of it. That means here this path is on the real axis. Do loci exist or not? So I see right of this path. Right of this path there is one pole. That means it's odd number of poles. Odd sum. So there's only one pole, so it's odd sum. So that means if there is a loci. If there is a loci, from where it will start? If there is a loci, for sure the loci starts from the poles. But which pole? All the poles. There are two poles here, so from both the poles the loci will start. And they're going to start and going to intersect here, and they're going to break. So they're going to break. So this is a breakaway point. It will be present somewhere in between there. So it's a breakaway point. I'm not finding the breakaway point and all, but I'm just imagining how, I'm just trying to sketch how it is going to look like. The sketch itself, I can say, okay, it's going to break. And where it will go? It is going to obviously go to the zeros, right? The loci travels from poles to zeros. From poles to zeros. Okay, good. If there are, if suppose a system has only one pole and there is no zero at all, where will the loci go? To the left of this there is odd number, so there is so the loci is going to be in the real axis. It's going to go to infinity. Why? Because there is no pole at all. I'm sorry, there's no zero at all. So the system assumes, or our root locus concept assumes that the zero is present at the infinity. Zero is present at infinity. That's what it assumes, infinity, or a concept assumes like that and goes till infinity. Okay, this is just for the understanding or just a bit of information. All right, so now I'm going to law the loci. So where it's going to break away and going to come, and where it's going to go to the zeros. Okay, it's going to go to the zeros. So if I just have to draw it like this, it is. So from where? So okay, because it's starting from the pole, the value of k will be 0 at the pole and keeps increasing. K equal to 1, 2, 3, like that. K equal to 5, and at the 0, wherever the 0 is at the infinity, right? So at this k will be equal to infinity. Okay, this is an imaginary 0 for this particular example given. It's not. It is just for the understanding. But here Here is the 0. So at this point k will be infinity. Okay. So here at the pole the k will be equal to 0. And at the imaginary axis, what is the k value? They have given the question. It's 1.5. We don't have to worry for now for this question. Okay, both the sides. It's a mirror image on the top and bottom. That is with respect to the real axis. Real axis is sigma. Alright, till this it's clear. So now tell me when the system is stable and starting from the pole, so the arrow mark will be pointing like this. The system or the path of the loci or the path of the root locus. Root locus means the path of the roots. Roots are the poles. Roots are nothing but the poles. Okay. So it is in the right side. It's starting from the right side. Once it hits the imaginary axis at k equal to 1.5, after that it's going to the left side. For the values of k greater than 1.5, the loci goes to the left side of the S-plane, which means that for the values of k greater than 1.5, the system is stable because if the poles are in the left side only, the system will be stable. That is the stability criteria. So that we can say the answer for this is A, where the k value is greater than 1.5. Okay, thanks for watching, and please do put your comments, and if you have any suggestions, please put in the comment section. Thank you so much for watching again.